listeners. Today, my guest today received her PhD in the history and philosophy of science from University College London. She has been a professor at several universities, including, but not limited to, Virginia Tech and University of Hawaii. She has held other academic posts more recently at the National Autonomous University of Mexico and as a visiting scholar at the University of Texas at Austin. She has written numerous articles on the history and philosophy of geology and is author of the phenomenal book From Mineralogy to Geology, The Foundations of a Science, 1650 to 1830, as well as Cuisine and Empire, Cooking and World History. Her work is as wide-ranging as it is comprehensive. Her ability to contribute novel analysis to every field she contributes to is remarkable, and I'm thrilled to have Professor Rachel Laudan here with me today in virtual space. Professor, how are you doing in these tumultuous times during this national pandemic?
I'm one of the lucky ones because I don't have to go to work, and I live in a leafy green suburb where it's safe to walk. So I'm doing quite well, except that I miss friends, family, and libraries. There you are.
Yes, yeah, of course, me too. I definitely really enjoyed visiting various bookshops, and now obviously since we're supposed to stay inside and of course follow CDC guidelines, I haven't been able to do that. But that's sort of part of the inspiration for why I invited you here today with me in virtual space, and I'm really appreciative that you were able to join me. Now, before I get started to the first question, I wanted to say that one of the things about your book, From Mineralogy to Geology, that I really appreciated was how it established Abraham Werner as a dominant figure in geology. Since I'm still in my undergrad sort of education in geology, one of the things I noticed was that the name Charles Lyell pops up a lot. And that's actually quite problematic because after reading your book, I realized how many other figures in geology actually played a role. And so I just wanted to say that seeing Abraham Werner and his contribution of the geological formation and sort of the temporal notions that he ascribed to that particular phenomena was very, very illuminating and very really interesting to learn about. Now, with that being said, one of the things I also noticed in my geological sort of undergrad career is that I was actually quite struck by the amount of concepts that we had to learn without really given the historical context of these contexts. I already mentioned the formation, the geological formation, and as well as others though. There's also Steno's laws and also uniformitarianism, which is a really big concept we'll get to later. But these omissions are obviously understandable during class because there's so much content to learn. So with that being said, in your view, as a historian of geology, would you appreciate possible development of history of geology courses that are actually embedded in geology undergrad coursework as well as graduate coursework?
Well, let me go to my experience as a student to answer that. Because the answer is both yes and no. When I was an undergraduate studying geology, for some reason, we all had to take, at the end of the 3 years, a course in the history of science. It was a general course in history of science, and so we had a faculty member do history of physics for a couple of weeks, and then we bounced on to history of chemistry and biology and geology and so on. It was excruciatingly boring. And I am a historian. I turned myself later into a historian of science. But it was, for each of these people, it wasn't something they particularly wanted to teach. It wasn't close to their interests. And they taught it as a series of discoveries. Well, here Robert Boyle discovered Boyle's law, and this was just before Newton came along, and, the Principia. And then there was and trying to do something with this. As I prepared for my final exams, I went into the libraries and I discovered a little book called The Architecture of Matter by Stephen Toulmin and June Goodfield. It was published in 1962 as part of a project to encourage the history of science. And my signature there, tell you something, 1966. So this is 54 years ago. This was quite different. This was actually mainly about matter theory, physics and at the border of physics and chemistry. And it told it as scientists working in great traditions, atomism on the one hand versus continuum theories on the other, and debates that went on over years, decades, sometimes hundreds of years, between very basic fundamental positions. And it also presented these debates not as something that was bad, but as something that led to very productive research. Because if one tradition made a big advance with some new investigating a new kind of area or developing a new way of analyzing old data, the other tradition would try to come up with a response. And so this interplay between kind of big overarching ideas and day-to-day research practice, according to these authors, was a very useful and productive feature of science. And it was one that I had completely escaped, both as an undergraduate in geology and in my history of science course. And so that's what I was partly trying to do for geology in my book, From Mineralogy to Geology. I wanted to ask, you know, what were the big overarching issues that shaped the thinking of people about the Earth at just the time when geology was becoming a very well recognized part of science and the way to investigate the Earth. So if you could have a course that addressed some of these foundational issues, that would be great. If you had the kind of course that just said, well, there was Hutton, and then there was Werner, and he wasn't very smart, and then there was Cuvier, and then there was Lyell, and then there was Darwin, I don't think it would teach you very much. I don't think you would get that kind of course now because history of science has developed. But I'm not sure that the way it's developed in the last 20 or so years would also be terribly useful, because it has history of geology, history of science in general, has become caught up in the questions that are occupying almost everybody at the moment. Questions about excluded gender, women like me in geology. It wasn't that easy being a woman in geology in the 1960s. Race, which races can and cannot or have or haven't been contributing to the earth sciences. Now, those are very important questions. They're very important for society about who gets access to being able to contribute to knowledge. But they're not questions that are going to tell you much about the foundations, the basic working assumptions that geologists hold and that are so foundational that often geologists don't bring them to the surface. They just, like uniformitarianism or formations, they just assume that you've absorbed these because they are so very, very fundamental. So there's my complicated answer. Yes, there could be some really wonderful courses. I think for paleontologists, the work that Martin Rudwick did years ago on the meaning of fossils is fantastic. and that would be very useful interplayed in a paleontology course, I think. But if it's the old-fashioned history of science as a sequence of discoveries, or if it's the new history of science as concerned with social justice within the sciences, I don't think it would really contribute to learning about research in the earth sciences. Does that make any sense?
It does. It does. Yeah, it does. And what I got, some of what I got from what you just said is that basically when I read your book From Mineralogy to Geology, I did notice you spent quite, for good reason, I think, quite a lot of time going over the sort of philosophical and kind of the logics that were deployed. So like inductive reasoning. I think the Veracaza method, true causes, sticks out to me. It seems like you spent a lot of time going over the sort of intellectual kind of underpinnings of what the geologists were deploying when they were thinking about the Earth. And from what I got from what you just said is that basically you'd want a course, ideally, if you were going to have a course, you would want a history of geology course that wasn't just a parade of names. It also situated the intellectual context that these men and these gentlemen, unfortunately, exclusively just gentlemen, were working with when they were thinking about the Earth.
Yeah, yeah, exactly.
Right.
And I mean, particularly at the beginnings of geology, it was such a radical step to do a historical science, because it broke with the idea that the only knowledge worth having was knowledge of eternal verities or eternal objects, the true essences of things. And instead it placed time at the center. And this was an unbelievable, I mean, we take it for granted now, but it was an unbelievable switch.
Yeah, that's and that's sort of the answer I would have hoped to have received. I mean, because that is my experience initially, is that the classes were really just parades of names and kind of this very half-baked understanding of the terminology. That it is, I think, reassuring to hear that if we were going to have courses, they would be as in-depth as you have elucidated they should be. Now, we kind of touched on uniformitarianism a bit, but I actually, for any viewers listening, a big part of this project of mine, and one of the reasons why I invited you here today, was partly geological education. And one of the things that I noticed as I started to read your history, which was actually the first history of geology, nonetheless history of science that I read, that was the first history of science I ever read, was basically I noticed when I read through these geology histories, these isms would come up: catastrophism and uniformitarianism. They come up quite rampantly. And one of the confusing things actually about these terms is that I think there are so many different conceptions of these terms. I can give you one conception by Stephen Jay Gould. He defines uniformitarianism as a dual concept. So substantive uniformitarianism and methodological uniformitarianism. So the substantive version of uniformitarianism he defines as, quote, a testable theory of geologic change postulating uniformity of rates or material conditions, end quote. Now, his definition of methodological uniformitarianism is, quote, a procedural principle asserting spatial and temporal invariance of natural laws, end quote. So basically, methodological uniformitarianism is talking about how the natural laws that we see today haven't changed at all the past several billion years, arguably since the inception of the universe. And then we have catastrophism, which is associated with, just like the term, catastrophic sort of geological events. You could think of possibly volcanism. You can think of bolide impacts. Can you actually, before we get to this question, do you have any kind of your own sort of definition of what these two terms mean initially? I know that there's so many different conceptions of them. Do you have your sort of own kind of quick definition of them?
I don't have a quick definition, but I do have a quick orientation.
Okay.
The one of the basic questions in all of science, not just in geology, is how you move between things that you can observe and the kind of conclusions or theories that you draw from these observations, which often involve things that you can't observe. Okay. In the 18th century, 17th and 18th century, and this in part goes back to this little book here, there was a long debate about what underlay gravity or the behavior of gases. Was the atoms or corpuscles, as they might have called them then, or was there instead some kind of continuum, some kind of ether underneath? And you could observe the behavior of gases, and you could observe the behavior of light, and you could observe apples falling to the ground. But how did you make the jump to what was the underlying cause of the behavior of light or the behavior of gravity? Was it little objects banging against each other, or was it some kind of wave phenomenon? And so people had different answers to this. This is where you get into induction and the method of hypothesis and the method of true causes, which we'll get back to. The same question comes up in geology. But there, very often, it's not a question of moving from the large-scale visible world to an invisible world that even with a microscope you can't reach, but instead of moving from what you can see at present to what was going on in an increasingly distant past that you've got traces of, but you don't have direct access to. And so people are asking themselves, what can we say about this? Now, let me get back to Steve Gould and uniformitarianism and catastrophism. Just as science works with big traditions, so does history of science. And the wrote those quotations in the 1960s. There was only one history of geology really available, and it was a book by Charles Gillespie at Princeton called Genesis and Geology. And it's a very fine book, but it's a fatally flawed book. This great book, which was set up as a struggle between the forces of reason, that is James Hutton and Charles Lyell, against a retrograde group of aspiring geologists, but who were overly influenced by the Bible, and who particularly were overly influenced by the idea that had been a great flood at some point in the past, the Noachian flood, Noah's flood. The trouble with Gillespie's analysis was that this debate was not between Christian geologists on the one hand and let's say agnostics or atheists on the other. It was between two different sets of beliefs about the kind of role that a divine being had had in the world. It was true that many geologists were Christian, and they did take the Bible as one potential source of evidence. There was no reason why they shouldn't really, because we can take written evidence and it takes a long time to sort out whether it's reliable or not. And on the other side were Hutton and Lyell, but it wasn't that they were not interested in a divinity in the universe. They did, but their divinity was just not a Christian God who had created methodological uniformitarianism, the belief that the laws of nature are constant. Lyell and Hutton believe the laws of nature are constant, and so did Cuvier and Werner and all the other people who are now called catastrophists. No debate about that at all, except for one thing, and that was the origin of new species. Because there was, by the 1820s and 1830s, really very good evidence that species had not been constant across the history of the globe, that some species had disappeared and other species had appeared in the geological record. And there, again, there was no difference. Both sides believed that the divinity had intervened in Earth history at certain points in order to introduce new species. The group that are now called the catastrophists thought that the deity, the Christian God, had intervened at intervals to introduce ever more complex species, culminating in the human species. Hutton and Lyell, on the other hand, but particularly Lyell, Hutton doesn't say much about this, Lyell believed that although individual species went extinct and were introduced, that classes, the bigger taxonomic category, had always been represented in the history of the Earth. And his argument was, we don't always see it, we can't, things get destroyed in the geological record, but that every time a class of, or the individual species in a class went extinct, God came along and introduced a new set of species to replace them in the same class. A lot of his work on the tertiary is about that. So if you go back to what people are debating about at the foundations of geology, they are much closer than the standard story suggests. Now, what do we say about definitions of uniformitarianism? I would just happily get rid of the word.
Okay.
It was introduced by William Whewell. William Whewell was the great panjandrum of 19th century science. He was master of Trinity College, Cambridge, where Newton had been. He wrote himself on mineralogy and many other aspects of science. He was one of the first people to write on history and philosophy of science. He was the man who invented the term scientist that we still use today. There was no word for somebody who did science before then. And he was a friend of Lyell's, and he reviewed the first volume of Lyell's Principles of Geology, and he described Lyell's position as uniformitarian. He did not agree with Lyell, but he thought it was a very fine piece of work. That's where the term uniformitarianism comes from, and it wasn't much used in the 19th century. It really comes in the beginning of the 20th century, when Archibald Geikie, who is a Scot like Hutton and Lyell, wants to boost their reputation, and in his book, The Founders of Geology, reintroduces the term uniformitarian and gives them a very special position. This is after Darwin, and after Darwin, the history of geology becomes warped by the fact that Darwin was so important. So I'm not sure that uniformitarian actually does much work for geology. I do think there's a very interesting issue connected with what Gould called substantive uniformitarianism, and that goes back to this vera causa business that you mentioned. Vera causa means true cause. And again, we have to see what was going on in Lyell's mind. Lyell is concerned with this question of how we can make reasonable assertions about what happened in the past, given that so much of the past cannot be observed. And so it's not, I mean, although we're talking about past and present, the underlying issue is not past and present, but observable and unobservable. And Lyell was a Scot. He was impressed by the Newtonian tradition. Newton was not an Orthodox Christian at all either. And Newton's ideas, Newton was the one who came up with this idea of a true cause. And a true cause was one that not only it had to be known to exist, and it had to be known to be adequate to produce the things it was supposed to have caused. And so that for him elevated it above other things. Let me give you an example. Supposing you say, what caused the extinction of fossils? You could say there was a great flood. If there was a great flood, then it would have caused fossils to have gone extinct. We know fossils went extinct, therefore there was a great flood. Now that's called the method of hypothesis, and scientists use it all the time. But the trouble is, we don't have any evidence for the Great Flood. Or we did in the, we might or might not. We've got, and what Newton wants to say, what Lyell wants to say is, do we have independent evidence that there are great floods? Actually, Lyell thought there were. He had this theory that one day Niagara Falls would work back to the Great Lakes, and boy, there would be a massive great flood across North America. So he was very happy with great floods. And is this adequate to cause the extinction of fossils? Yes, says Lyell, a great flood of that kind would be adequate to make species extinct when all the waters of the Great Lakes come pouring out. Lyell picks up on this and says, well, the only causes that we could really assert about the past are ones that we can observe at the present and that we know would produce the effects. That's what he meant by uniformitarianism, a word Lyell never used. And that seems to me not a bad set of rules. Lyell is seeing himself very much, he was not a modest guy. The principles of geology, Newton had written the principles of natural philosophy, and Lyell is picking up his method, and actually Darwin does the same thing. Darwin wants also to be a great man, and he picks up the vera causa method. So that's what's going on there. But whether that's a useful thing today, when you're just told today that, oh, the present is key to the past. Well, yes, but only if you understand it precisely, because otherwise it's just sort of violins off. You can make anything of it that you want to.
Exactly, right. And
so, yeah.
So,
So that's my take on uniformitarianism.
and that seems to be quite in line with Gould's paper. His paper, Is Uniformitarianism Necessary? He eventually surmises, I mean, it's really interesting actually that you both kind of come to the same conclusion, at least to my reading, because Gould says that basically we need to take uniformitarianism and retire it. It's just not effective anymore. It's a term best used to understand in the historical context of when it's applied. So then that kind of leaves me with this thought about sort of catastrophism. And, you know, when one does the basic kind of, just to continue on really quick with this question, when we type in catastrophism, let's say, on the computer, we get, as I stated earlier, you know, things like bolide impacts and the mass extinctions of the dinosaurs and whatnot. What role does this kind of understanding of these sort of apocalyptic type events play in our understanding of geology today? Do you think that it's particularly in the same way that it's not helpful to really have uniformitarianism floating around today? Is it also kind of just irrelevant and not really functional to have catastrophism today?
I think that's an empirical matter. If it really is the case that you know, meteorites impact the Earth and cause very dramatic changes, and if you want to call that a catastrophe, you can.
Right.
If you want to say that there can be massive volcanic outbursts, and you can produce evidence that this has really happened, yeah, I don't, and I mean, as I say, this is, if you go back to I mean, there's nothing that's even, that most classical uniformitarianism of Lyell did not rule out catastrophes. I mean, he's quite prepared to have catastrophes.
Right. Okay.
So,
Yeah.
yeah, I mean, there's nothing, there's no reason why Earth history should have been, you know, mellow all the way through.
Right.
You don't want to say there's been a very dramatic event unless you've got good evidence for it. But if there's good evidence, sure. But whether you, I would probably avoid the word catastrophe again, just because it summons up this, what seems to me not helpful. It wasn't a very helpful dichotomy at the time in the early 19th century, and we're now in the 200 years later, you know, no.
Right. Okay, I see. That really, I think, provides a lot of clarification and kind of assuages some of the confusion I had with these terms. It does seem to me like these terms are so loaded with historical meaning that invoking them today just causes a plethora of problems. But I do know of a theory that is quite actually quite modern, especially in my view of the history of science. It actually seems to me like the theory of plate tectonics is actually the most recent major scientific theory. When we look at geology, it looks to me as if the premier theory of geology, right, is plate tectonics. And just really quickly before I get to the question, I had this conversation with Victor Baker. I'm not sure if you're familiar with Professor Victor Baker, but I had an email correspondence with him, and I came to this conclusion, and I was asking him, you know, kind of what he thought. I said, to me, you know, it looks as if the philosophy of geology isn't as populated as it could be. And I speculated that that could possibly be because the primary theory of the field of geology wasn't really developed or discovered until the 60s. I mean, even for linguistics, even the scientific study of linguistics, you know, generative grammar from Noam Chomsky, that came in the 50s. So geology is really late in the game when it comes to its foundational theory. And the question would be, what makes plate tectonics the premier theory of geology. Why is discovering
Oh gosh.
activity so important?
There's a lot to say about that. I do think there was a theory beforehand that often is described as catastrophist. Most of the 19th century, the general theory was of a contracting Earth. And there was very good physical evidence for that. There was astronomical evidence. The idea was that as the Earth contracted, mountain ranges would be thrown up, and also there would be flooding. And it was a very well-founded theory. You might enjoy Mock Green's book, I've forgotten what it's called, on sort of geophysics through the 19th century. That kind of fell apart in the early 20th century. And there was a period when I was an undergraduate where there was no overarching theory of geology. And when I was a student, you did, petrology and petrography and mineralogy and crystallography and geomorphology and paleontology, but it was in a way very unsatisfactory. And then really very suddenly, I had finished my undergraduate degree and I bumped into I was going to become a geologist and I decided to go into history and philosophy of science instead, but I bumped into one of my former professors and he said to me, "Rachel, have you seen what's happened in geology?" And I said, "No." I hadn't gone into it in part because at that stage, doing a graduate thesis meant doing a survey of 1 square mile of the Earth's surface. And I wasn't at all sure that that's what I wanted to spend 3 or 4 years doing. So he said, "Well, I think you should go and read Scientific American," which was still a respectable journal at that stage. And wow, there was this article by Tuzo Wilson on plate tectonics. And oh my God. It was a tremendous shock to geologists. It caused a lot of heart searching because how could they have been so wrong? But why was it so important? Well, one, it made surprising predictions, which had not been thick on the ground before in geology, and now things like magnetic stripes and geomagnetic reversals and so on were things that the theory predicted and were found to be true. And it also pulled together an enormous amount of evidence about the grand structures of the Earth, the volcanic arcs and then what became known as subduction zones, but they hadn't, earthquake areas. It was not simply a case of, oh my God, we've always had continental drift, and why were geologists so dumb as not to realize that continental drift was the true theory? Because quite apart from the massive amounts of new evidence that underpin plate tectonics, it's not the same theory as continental drift. Continental drift posits that the big divisions on the Earth are between continents and ocean floors. Plate tectonics posits that the big divisions in the Earth are between plates, and the areas where plates are created and the areas where plates are destroyed. And those do not map neatly on to continents and oceans. Sometimes there are long continental ocean divides, but that's not always the case. So it was a new theory, and it made surprising predictions, it explained a lot. And after a period of 30 or 40 years where geology had not had an overarching theory, it now had one.
And And that overarching component, the reason why it's described as being this kind of overarching, theory is because it basically explains volcanism. It explains volcanism on the margins of the plates, and it also explains various different rock packages. Would it be valid to say that everything in geology that you learn in sort of a geology education directly or indirectly descends from actions from plate tectonics?
I don't think it descends from it. There's a lot of stuff that isn't deduced from plate tectonics. That plate tectonics can explain it, but it doesn't follow from plate tectonics necessarily. And I think there are things probably about, say, continental interior processes that plate tectonics doesn't explain. I think sooner or later, yeah, it will have to be modified in various ways. But for now, it's, far and away the best we've got.
Right. Okay, that is quite an explication on plate tectonics. And I see that actually you have a paper, Tensions in the Concept of Geology. Really quickly, I wanted to mention, you talk about how plate tectonics actually is a point of flux for the shifting of sort of the kind of intellectual sort of animus of geology. In other words, it's a time when one of the things you have in the paper is natural history or natural philosophy, where geology kind of fluctuates to trying to, I guess, characterize natural history, geohistory, to more causal mechanisms. Is that correct? Is that a fair characterization of
Yes,
this?
and I mean, it did involve a shift in the disciplinary orientation of geology, away from the traditional geologists towards the geophysicists, and there was a good bit of tension around that.
Yeah, that's very, very fascinating stuff there. Plate tectonics is something that I'm particularly interested in. So I'm glad to have asked you that and got the explication that I did. I do want to switch gears here and move on to your book, From Mineralogy, very briefly. You have a point here. You have a chapter that talks a little bit about mining. Just a point about it. It's question 3, it looks like, or question 4, actually. In your book, on page 55, you write, the systematic mineralogy taught in the mining academies, as opposed to surveys of existing techniques, probably did little to stimulate industrial development in Europe. However, the converse was true. Industrial development stimulated theoretical mineralogy by providing jobs in mining schools and mining services. And then later you go on to state, science thus benefited from institutionalization, end quote. So when I read this, these sentences here, I interpret that as saying that there was sort of an asymmetrical relationship to geological theory during this time, in that the institutionalization of mining contributed to geological theory. And this is kind of interesting because today it almost seems as if we're taking like the latest instrumental techniques, whether it's like X-ray powder diffraction or other sort of laboratory methods, and we're applying those methods to resource extraction. I just wanted to know, do you think that your thesis regarding the relationship between mining and geological theory and development has been reversed in today's world? Even if it has been reversed or not, I think there's still a very interesting relationship that you write in your book regarding the relationship between mining and geological and mineralogical theory. So what do you make of this relationship today?
Again, you have to understand the situation when I was writing this book. At that point, the standard view in history and philosophy of science, and indeed more generally, was that technology in general was just applied science. Science came first, and then people went out and applied science to build the atom bomb or, make electricity or what have you. And so given that geology was institutionalized in Europe at the same time as the Industrial Revolution came along, a lot of people said, well, geology was one of the causes of the Industrial Revolution. It, allowed the building of canals and railroads because people knew where strata were, and it allowed the development of mining because people now had a tool to know where minerals were. And that actually wasn't the case at all. People were building canals and extracting minerals quite happily without the benefit of geology. Geology, as it developed, particularly in England, was a kind of gentleman amateur activity. Mining was very active in Germany and France. Well, it's a different kind of mining. In England, most of the mining was soft rock mining, coal, and in Germany and elsewhere, there was much more hard rock mining. And the hard rock mining was highly institutionalized. It had mining schools and so on and so forth. But those were there long before the theories of geology came along. What the mining schools allowed was a place where people who were interested in the earth could get paid positions to think about questions of, geological questions. And so Werner's disciples, for example, were able to get paid positions and work on issues in geology, which was, at a time when there weren't many positions for scientists, was very, very important. Now, today, I think most people think there's a huge area that you might call technoscience. Mm-hmm. That's one of the words people use, where it's very hard to tell the difference between science and technology. Mm-hmm. The kind of very modern instruments and so on, where do you draw the line? It's not clear that there's a sharp distinction between theoretical science and practical mining, for example. And I think that's where I'd say there. But this was the way I set those issues up was to counteract the idea that particularly English geology, which was a highly elite amateur activity by rich gentlemen, had anything to do with the Industrial Revolution. It had very little.
Beautiful, beautiful. Wow. Okay. That's, yeah, I definitely really wanted to get some more kind of expansion on that part of your book, because I think that was a particularly interesting kind of intersection between industry and science. So Professor Laudan, I really appreciate you taking the time to meet with me. This was an amazing once in a lifetime experience and interview for me.
No. You'll have many more lifetimes to do.
You are a huge inspiration to me, and anybody listening that is interested in the history of geology and geology just by itself needs to get this book, From Mineralogy to Geology by Professor Laudan. It is an amazing book. It answered so many questions to me that I had, and it got me started in this passion that I have now for the history of geology. For that, I'm going to be forever grateful to you, Professor.
And I'm grateful for the chance to talk about it after so many years after I wrote it. Thank you very much, Vincent.
Of course. Thank you very much, Professor. Have a good one.